So if you remember, we were talking about confidence intervals. Okay? And so for example 3, we went through it and we found a confidence interval, 31.33 to 31.78. So we said we're 95% confident that our population mean is between these two numbers. Okay? Now this next part is very important because it is the most commonly misunderstood thing in statistics. Okay. Something that will come up on your test somehow. So we found that our 95% confidence interval for the population mean gas mileage is 31.34 to 31.78. Now this does not mean that the probability is 0.95 that the true mean falls between these two values. Okay. The reason why is that your true mean is a fixed value. It doesn't change. Okay. If you actually knew all the data in the population, then you could find the population mean. So there's no probability attached to the population mean. What is the probability attached to in this situation? Okay. The probability is attached to which sample mean did you choose. Okay. So to see that, let's go back up and look at the applet that didn't work yesterday. So here's the distribution. Okay, notice we have the normal curve. This is the distribution of all of our possible sample means. Okay, so this curve is for all of our possible sample means. Okay, so let's say we want to take a 95% confidence interval. What happens is I find one sample mean. You probably can't see it on the monitor, but in the middle of the line, there's this little red spot. That's your actual sample mean, and then the line represents the confidence interval. Okay. Notice that this green line represents where the population mean mu is. So our confidence interval does contain our population mean mu. If I take another sample, notice that my sample mean changed. It came over here. But my confidence interval still contains my population mean mu. A third sample, let's keep sampling. Okay, so notice how on each sample, my sample mean changed, but my confidence interval still contained my population mean mu. However, what happened on this sample? It doesn't contain the mean. Why doesn't it contain the mean? Okay, because the sample mean that I picked was so far out in the tail that the confidence interval isn't going to cover the mean. Okay, so when we talk about the probability, the 95% attached to our confidence interval refers to which one of the sample means I happen to get in my sample. So did I get a sample that happens to give me a sample mean that contains that gives me a confidence interval that contains my population mean? Or did I get one of the sample means that was so far out in the tail that once I found my confidence interval, it doesn't actually contain my mean? Okay. So we can sample lots of them. So if I do another 50, notice that most of the confidence intervals do contain that population mean, but a few sample means were so far out there that our confidence intervals don't contain the mean. Okay. If I do lots and lots of confidence intervals, notice what is my percentage of confidence intervals that contain the mean? 95%, which is why we call it a 95% confidence interval. If I switch these to 99% confidence intervals, then you would expect to see about 99% of the confidence intervals contain the mean. So let's do it many, many times because all of our probabilities are over a long time. Notice, again, 99% of my confidence intervals contain my mean. Okay. Questions about that? So that's what this warning is talking about again. So remember, it wasn't that mean that changed. The population mean didn't change. It was where my sample mean was. That's what actually changes, and that's what the probability is attached to. So let's try another example. Assume a sample of 100 bank customers has a mean waiting time of 5.46. So that was a sample. We had n equals 100. The sample mean, that's an x bar. 5.46. Assume the standard deviation of all bank customer waiting times. Does that sound like a sample standard deviation or a population standard deviation? Population, where they said all. So that's the sigma equals 2.47. So now I want to have you actually compute a 99% confidence interval. So if you looked up at your notes, the formula is x bar plus or minus our critical point times the population standard deviation over the square root of n. So what's the only thing in that formula that I don't know yet? The critical point. How do I find a critical point? Okay. Let's start by drawing a picture. Okay. How much area do I want in the middle? 99%, so 0.99. So how much is going to go in each tail? If I do 1 minus that, I get to 0.01, and then I have to divide that by 2. 0.005, correct? Okay. And I need to find the z-value. That's alpha over 2. That's the symbol they use. I need to find what z-value makes that happen. Or I could find the negative one, since that might be easier to do, since our table always gives us areas to the left. So go to your standard normal table. Hopefully you guys all picked one up so you have it in front of you so you can try too. And I'm looking for an area 0.005 in the left. So what is the closest that you guys see? Okay. So it looks like it's evenly between 0.0051 and 0.0049, so z is between negative 2.57 and negative 2.58. You could pick one of those. I'm just going to go with the average of the two since it's evenly in between. So this is negative 2.575, and this is positive 2.575. Now if we wanted to, we could use a computer and they could give us a more exact z-value without having to just take the average. Okay, so now let's plug everything in. So x bar is 5.46 plus or minus my 2.575. Now what would happen here mathematically if you accidentally use the negative 2.575? Okay. You'd get the same thing, because whether you add a negative and then minus a negative, or add a positive and minus a positive, you're still going to end up adding and subtracting each time. Okay, sigma is 2.47 over the square root of 100. So it's 5.46 plus or minus 0.636. What do we call the part that we add and subtract for my confidence interval? Remember? The part that we add or subtract is called our margin of error. So when I put this in my calculator, I get that it goes from 4.824 to 6.096. So that's how you find a confidence interval. Questions on the computations to find it. Okay. Do you remember how we interpret it? Okay. So to interpret it, I'm going to say something like, we are 99% confident, okay, that the population mean, or if you're going to talk to your boss, put it in a little more context. So the mean of what? What was our population? The population is probably all bank customer waiting time, so we're 99% confident that the mean waiting time for all customers is between 4.824 and 6.096 minutes. So we've actually narrowed it down quite a bit here, I think. We're pretty sure that the mean waiting time for all customers is between 4.8 and 6 minutes. Now, does that mean that every customer that comes in is going to be between 4.8 and 6 minutes? No, okay, and that's what a lot of times people try and do. They try and say, well, all the individual values are in there. No, we're 95% confident that the mean is in that range. One person might have to wait 1 second, another person might have to wait 10 minutes. Okay, but we're 95% confident that the mean is in that interval. So let's remind ourselves, what does the 99% confidence level itself mean? So not the interval that we found, but the confidence level. What do we mean when we say 99% confident? What is that 99%?
It means we're 99% confident that the actual sample mean is within, or the actual mean is within our sample.
Okay, and what makes us 99% confident? Like, what is that 99 itself actually attached to? Does that make sense? Okay, so what is the thing that can change? So in the applet that we looked at, what can change? Can the population mean change or the sample mean change? The sample mean. So when we say this, it's of all the possible samples, okay, 99% of the sample means would give us a confidence interval that contains the population mean mu. Do we know if our confidence interval is one of those 99% that actually contains our population mean mu?
That's 99% confidence.
We don't know, but we're hoping that it's one of those 99%, which that's pretty good odds, right? Only 1 in 100 chance that you got a bad confidence interval. But in real life, you really have no idea whether or not you have one of those good 99 intervals or the one that didn't work. So looking at our interval, okay, do you think it's plausible that the mean waiting time is less than 5.5 minutes? Okay, some people saying yes. Go ahead and talk to me. Do you think it's plausible that it's less than 5.5 minutes? Yes or no?
Yes, because that would still fall within our 99% confidence.
Okay. So 5.5 minutes does fall within our confidence interval. Does like 3 minutes fall within our confidence interval? Okay. I would look at this and I would probably say something like, well, 5.5 is in there, so it could be less, but it could also be more because my confidence interval does go above 5.5. So I'm not going to say, I'm not quite sure. We don't actually have enough information here, I don't think, to know. How can I narrow down that confidence interval and maybe know for sure? Take a larger sample size. So I don't know, since some values in the confidence interval are greater than, I wanted to say less than first, are less than 5.5, but some are greater than. Okay. Now if I just asked you, do you think that it's possible that 5.5 is plausible? I'd probably say, yeah, 5.5 is plausible because it is in the confidence interval. But as far as less than, I don't really know if it's less than because it could also be greater than. So, any questions so far? So our next page, we're going to talk about the length of our confidence intervals. So due to a lot of past data, we can safely assume that the standard deviation for the population of credit card debts for college students is $3,500. Find the margin of error for each situation. Notice what they did there. It's like we've talked about how if you don't know the population mean, you probably don't know the population standard deviation. But one of the ways that you can say you know your population standard deviation is you can estimate it from past data. That's probably the only situation in real life where you would ever say that you know your population standard deviation. So let's find the margin of error for each situation. So let's say we have a sample size of 300 and we want to find a 95% confidence interval. Okay. First of all, if I want to find a 95% confidence interval, I need a critical point. So 95% confidence interval means I need 0.95 in the middle. So that's 0.025 in each tail. And we go back to our standard normal table. I'm looking for 0.025 in the middle. So 0.025 looks like z is negative 1.96. Pretty soon you'll probably memorize that. So my critical point is going to be 1.96, and then I need to find the margin of error. Remember, your margin of error is the part that you add or subtract. So it's going to be our critical point times the standard deviation over the square root of n. So 1.96 times standard deviation of 3,500 over the square root of my sample size, which is 300. Looks like we're at 396. Now let's change our sample size. So now I want to do a sample size of 1,200. I keep my confidence interval at 95%. So if my confidence interval is still at 95%, then my critical point is still 1.96. So 1.96 times 3,500 over the square root of 1,200. Gives me 198. So what happened to my margin of error when I kept everything else the same and I only changed my sample size? My margin of error went from 396 to 198. Okay, so here's a graphic for you where I drew out my confidence interval. For this is n equals 300 and the confidence interval for n equals 1,200. Okay. So you'll see as we increase our sample size, our margin of error gets smaller. Okay? And we want smaller margins of errors because that means that our estimates will be more precise, or our intervals are smaller and I get a better information out of them. So let's try the next situation. So now let's see, we have sample size of 1,200, sample size of 1,200, confidence level of 95%, confidence level of 99%. So my critical point for 95% is 1.96, and do you remember what we found for 99% for the previous page? 2.575, right? So let's find our margins of error. So 1.96 times the 3,500 over the square root of 1,200. And I think we just calculated that, so that should be 198. And then if I wanted to do it for 1,200 and 99% confidence, then it's 2.575 times 3,500 over the square root of 1,200. So 260. So what happened here? look at the picture. Here's my 95% confidence interval. Here's my 99% confidence interval. So what happens to your margin of error if you increase your confidence level?
Goes up.
The margin of error gets bigger. Okay, which makes sense when you think about it, because remember, what did your confidence level mean? It means how many of all the possible confidence intervals would actually contain your population mean mu. And so how could you make sure that more of your confidence intervals contain the population mean? You have to make it wider. Okay, so it's a trade-off. You'll be more confident that your population mean is actually in there, but your interval is going to be bigger, and so it won't be quite as precise. So let's summarize everything. So a high confidence level means that our method almost always gives correct results. It means that almost all the possible confidence intervals will contain the actual population mean mu. But a small margin of error says that our interval is precise and accurate estimate of our parameter. So do you see how we kind of want a high confidence level, but we also want a small margin of error? Okay, and so how can we get both? Get a larger sample size, because your larger sample sizes give smaller, more accurate confidence intervals. And so even though your higher confidence levels require longer confidence intervals, I should put it there, okay? If you take larger sample size, you can offset that and still get to your precise intervals. Questions on that? Does that all make sense? So we've talked about it quite a few times that we want to have a large sample size. Now the question is, how large of a sample size do you need? Lots of times in advance, the company will know, okay, if I'm estimating bank waiting times, I don't want to be off by more than 30 seconds. Or if I'm estimating how fast this prescription will help kill your headache, I don't want to be off by more than 20 minutes. Okay? So they'll know in advance how precise they want their interval to be, and then they can figure out how many people they need to go measure. Now, why don't they just go out and measure millions of people every time to make sure they get a really precise interval, or thousands of people every time? Time-consuming and expensive. So before we collect our data, we can choose our sample size to get a desired margin of error. Okay. Now, of course, we assume you already know your population standard deviation sigma, otherwise you couldn't use any of these confidence intervals we just learned. The margin of error is, oh, sorry, my z-star keeps coming in from my other notes. Okay, so your critical point times your population standard deviation over the square root of n. Okay, now this is the equation that tells you your margin of error. So if you want to figure out how big of a sample size you need, you just do the algebra, rearrange your equation, and solve for n. So you'll end up with this formula. Okay, so critical point times standard deviation over your desired margin of error squared. So for example 6, suppose we want to survey college students to find the mean credit card debt, and we know that sigma is 3,500. If we want our margin of error to be $150 or less, with 95% confidence, what sample size do we need? Okay, because they're probably not going to complain if you come back with a smaller margin of error, okay, than 150. So 150 or less. We just want to make sure we don't go over 150. So n equals, okay, so z star, we need our critical point. What is our critical point for a 95% confidence interval? 1.96 times 3,500. That's my population standard deviation over our desired margin of error, which is 150. Okay, square that. So 2,091.537. Okay. Can you survey 2,091.5 students? Okay, no. And so I want my 150 or less, so how do I make sure that I don't go over that margin of error of 150? Which way should I round this? Just make it a little bit larger. It's good to go bigger because that gives you smaller confidence intervals, which are always good. So we will round to 2,092 students. Okay. Now the company might decide to just round that off and say 2,100 students or something, and that would be fine. They just want to make sure they have at least 2,092 students to get that margin of error to 150 or less.
I have a question. I might have missed this. Is the margin of error plus or minus 150 or?
Yeah, the margin of error is the part that you add or subtract, so it's going to be half the length of your total interval. Okay. Your book lots of times will ask you for the length of the interval instead. And so if they tell you they want a length of 300, then you say, okay, my margin of error is 150. So keep that in mind as you do your homework. I do have one problem like that worked in, though, eventually. So that is everything for a Z confidence interval. Okay, so any questions? So the next thing to talk about is, well, what if we don't know our population standard deviation sigma? Because in practice, if you don't know the population mean, you probably don't know the population standard deviation either. Okay. So in practice, you're almost never going to use a Z confidence interval, but it's the easiest one to teach, so we usually start with that. So if you don't know the population standard deviation, what are you going to have to use instead? You would have to use the sample standard deviation. And what happened yesterday, we said if we switch from using the population standard deviation sigma to using our sample standard deviation S, what happened? Instead of a Z distribution, we have a T distribution. Okay. So first of all, standard error, so just a review of yesterday. So since the theoretical standard deviation of x bar is sigma over square root of n, we estimate the standard deviation of x bar by s over the square root of n. And this is called the standard error of our sample mean. Okay, so s over the square root of n. And again, once we use our sample standard deviation s, we have to use our t distribution. So here's our formula for a one sample t confidence interval. And you use a t interval if you don't know your population standard deviation. That's always the difference in this class. Anytime you ask me, when do I use a z-test, when do I use a t-test? It always comes down to this situation. Do you know the population standard deviation or not? Okay. So here's your confidence interval. X bar plus or minus. Okay. This whole nasty looking formula symbol is just our critical point. Okay. And then it's s over the square root of n. Notice it looks very similar to our last formula, except for I have a new symbol for critical point and I use an s instead of my sigma. Once again, this interval is going to be exact if our population is normally distributed or if my sample size is at least 30. Now, the t distribution, or t confidence intervals, t tests, it's actually so robust that as long as your data is definitely, unless your data is definitely not normal, you're going to be okay to use the t-test. So even if your population isn't quite normally distributed, as long as it's just like not obviously not normally distributed, you can still use the t procedures. So we're going to talk about how you can figure that out. Okay. And then just the last note, because your t distribution gets closer and closer to your z distribution as your sample size gets bigger and bigger, some books will say, well, if you have a sample size bigger than 30 or if you have a sample size bigger than 50, go ahead and use the z confidence interval instead. In practice, though, we just prefer to just always use the t confidence interval. If you know s, just use your t confidence interval. You're going to get just a little more accuracy, and it's less confusing to not have to worry about switching back and forth. So first things first, we have never used the t table. Make sure you have a t table from the front, and let's figure out how you actually find your critical points on a t table. Now the first thing we need to remember when we use the t distribution is that our degrees of freedom is n minus 1. So degrees of freedom is sample size minus 1. So if my sample size is 10, my degrees of freedom are 9. Okay. Now, to do these confidence, or the critical points, we're just going to draw pictures just like we did for the z-table. They're going to look exactly the same. So if I want a 90% confidence interval, that means I need 0.90 in the middle, and how much goes in each tail? Let's see, I have 10% left, so 5% for each tail, so 0.05. So for sample size of 10, 9 degrees of freedom, area in the right tail for 90% is 0.05. Okay. And now we need to go find our critical point. Okay, sorry, I copied these notes over, it's still a t-star. Okay. And we need to go to the t-table. The reason I asked you for the area in the right tail is because unlike the normal table, the t-table always gives you areas in the right. Notice their symbol. When they write the t, they'll first put the alpha, that's the area in the right, comma, and then degrees of freedom. So that's why our symbol for our t, alpha over 2, comma, n minus 1, that's why it looked like that. It's telling you how much area is in the right tail and your degrees of freedom. But in our situation, we have 9 degrees of freedom, and we want 0.05 area in the right tail. So it looks like we're at 0.1833. Oh.
Okay, how do you read this again?
So, let me back up. Okay, this is very different than the normal table. Not only is the area going to be in the right tail instead of your left tail, but we're used to our probabilities being in the middle, right? Okay. Now that doesn't work for the t-distribution because it has so many different degrees of freedom, so they changed the format of the table. Okay. Read down the left side, and that will tell you degrees of freedom. When you read across, notice it's the alpha. This is the area in the right tail across the top. So across the top is the area in the right tail, which means what is left to go on the inside. The things on the inside is your actual t values. So they changed the format quite a bit. Degrees of freedom, down the left, across the top is area in the right tail, and on the inside is your t critical values. Okay, so for our first problem, what are our degrees of freedom?
9.
So we want 9 degrees of freedom. How much area in the right tail?
0.05.
0.05. The intersection is 1.833. So it'll probably take a little while to get used to switching formats, but my critical value here is 1.833. Notice that critical value changes for every different degree of freedom. So just coming back to our picture really quick, so this value would be 1.833. What would this value be, just in case I ever wanted to know? Negative 1.833, right? Now, if I now wanted to do a sample size of 30 and still keep my confidence level of 90%, would it still be 1.833? No, because I'd have different degrees of freedom. Okay, so let's try the next one. So for sample size of 5, degrees of freedom are 4. I have 4 degrees of freedom. If I want a 95% confidence interval, okay, so I start with 0.95 in the middle. That gives me 0.025 for each tail. So when I ask you for the area in the right tail, that is 0.025. And now we go back to our z-table. So 4 and 0.025. So we're looking for 4 and 0.025. That puts me at 2.776. So for my next one, 14 is my sample size, so my degrees of freedom are 13. I want a 95% confidence interval, so how much area is in the right tail? It's still going to be 0.025. So I'm still, I switched to 13 degrees of freedom, but I still want 0.025 in my right tail, so it looks like I'm at 2.16. Now my next one is 34 for my sample size, so my degrees of freedom are 33. Okay. And I want an 80% confidence interval. So tell me how much area is in each tail? 0.10. So we go to the Z table, or T table. I'm looking for 33 degrees of freedom. Okay. Do you see 33 degrees of freedom on there? Okay. No. So what we're going to have to do is use one of the values that's on there, or use a computer. But since you can't use a computer on the test, we have to know how to use the table. So what we're going to do is we will always round down for degrees of freedom. For the T table. Why do you think I round down instead of like rounding up? Okay. What happens to your critical points as you go down on degrees of freedom? So let's look at my critical points. So let's focus on the column we're interested in. We want 0.10, so that's this right column, or left column. Okay, so let's see, starting at the bottom, 1.28, 1.29, 1.3, 1.31, 1.31, 1.313, okay, 1.318, 1.32. What's happening to my critical points? As I round down on my degrees of freedom, my critical points are getting bigger and bigger. Now, if your critical points get bigger and bigger, then that means your margin of error gets bigger and bigger as well. Your confidence interval gets wider and wider. Why would I want to make my confidence interval wider here?
Make sure you're incorporating area.
Okay, to make sure I'm incorporating my area, and I don't want to tell someone that my margin of error is smaller than it really is, because that would be misrepresenting my product if I go out and I say, oh, well, my margin of error is this small, but in reality it was actually like this big. So in practice, it's better to go with a wider confidence interval just so you're not misrepresenting it. Okay, so it's to be conservative. It might not be quite as precise as it really is, but you're not going to be saying, or you're not going to be giving yourself too much credit, kind of a thing. So we round down to our next degree on here, which is 30 degrees of freedom. And it looks like we're 1.31. Okay. And so let's see, round to 30. Okay. So at 50, my degrees of freedom are 49. What am I going to have to round that to? So look at your table. What's the next lowest? 40. Okay. If I want 98% confidence interval, then how much is left in each tail? 0.01. So 40 degrees of freedom, 0.01. $2.423. Did I write that down right? So that's how you actually find critical points. So we're missing that knowledge. And the other knowledge that we need to use are T confidence intervals instead of Z, is how can we tell if our data is normally distributed. So a normal quantile plot creates a scatter plot of our quantiles of your data set and the quantiles of a standard normal distribution. So basically it looks at your data set, compares the quantiles, and then compares it to the quantiles of a standard normal. So if your data is normally distributed, then the two quantiles should kind of match up. Okay? And you would get a straight line. So when you look at a normal quantile plot, if your points on the plot lie close to a straight line, then the data is approximately normally distributed. Okay? The closer it is to a straight line, of course, the more normal. And the further it is from a straight line, the more not normal. So we said that the t-distributions are pretty robust, so unless it's obviously not normal, you're good to go. So here are some examples where it's approximately normally distributed. Okay? Notice this one, pretty close to a straight line, fairly close, fairly close. You know, we have a few hiccups, but fairly close to a straight line. These ones aren't quite as close, but it's still mostly a straight line. Okay? Now here are ones that are obviously not normally distributed. Okay? Notice this, definite curve. S-curve, curve, really big curve. Okay? So those are definitely not normal. And that's the kind of scale that I'm asking you to use on your, when you do your homework or studying or test, is mostly normal, definitely not normal. So let's try an actual example. So one measure of a company's financial health is its debt-to-equity ratio. One bank wants to make sure that its mean debt-to-equity ratio is less than 1.5. To estimate their mean debt-to-equity ratio of the current accounts, the bank randomly selects a sample of 15 of its accounts. So it looks like my sample size is 15. Find a 95% confidence interval for mu, the true population mean of the debt-to-equity ratio, and interpret this confidence interval. So the first thing I did is I gave you some graphical representations of the data. Why would I need to give you the graphical representations? To see if it's normally distributed. Why do I need to check to see if it's normally distributed? Because my sample size is small. So remember on the t, it's the same rule as for your z distribution. You either have to start with a normal distribution or have a sample size of at least 30. Since my sample size is less than 30, I need to check and see if my data looks normal. Okay. So when I look at my histogram, it kind of looks like it was mostly normal, but we kind of had a hiccup here. But when you look at your normal quantile plot, it's a fairly straight line. So because it is robust, this is still normal enough for our purposes. So you looked at the normal quantile plots. Unless it's obviously not normal, like really far off from normal, we're going to be good to go. Now, part of the reason why is it's that we needed to have a normal population. Now, our samples that come from normal population, if you have a small sample, you might have a few missing pieces because your sample size was so small, and it might not look exactly normal. But as long as our sample looks at least fairly normal, then our population would have started off as normally distributed. So I know that it's normal. Let's see. Let's find our critical point. So my critical point, let's see, degrees of freedom is n minus 1, so 14. And area in the right tail is what? Let's see, we want a 95% confidence interval. So we want 0.025 in each tail. And for a z distribution, it would be 1.96, but the t lets us have a little more flexibility for our sample size. So we need to look up our t point with 0.025 in the right tail and 14 degrees of freedom. So that's the notation that they're using. Okay. What is it? Okay, so 2.145. And let's write down our formula again. So x bar plus or minus t alpha over 2. Why is it alpha over 2? Because every time to find the area in the right tail, we had to see what was left over and divide by 2. Okay, t alpha over 2, comma, n minus 1, because we had to take our sample size minus 1 to get our degrees of freedom, times s over the square root of n. Okay. Now, as far as finding the sample standard deviation, I'm not going to ask you to do that by hand. We're going to use software. So here's some output for Megastat. Count, that's your n sample size. Mean, that would be your x bar. and sample standard deviation would be your S. And so you can just pull all the values from the output. So my sample mean is 1.3433 plus or minus our 2.145 times S 0.1921 over the square root of 15. One 1.3433 plus or minus 0.1064. Okay. Did you guys get the same things I did? So we were supposed to find the confidence interval. We're also supposed to interpret the confidence interval. Okay. So we could say that we are 95% confident that the mean of what would be a reasonable population in this situation? The mean debt to equity ratio of all accounts? Is between 1.2369 and 1.4497. What was their original goal? Do you remember? Look at the problem statement. What was their original goal for the debt equity ratio? Less than 1.5. So do you think it is plausible that it is less than 1.5? I think so, since my whole confidence interval is less than 1.5. So they're meeting their goal, I think. Or at least plausible that they're meeting their goal.
Is there ever anything we do to like a confidence interval that's like one-sided? So like anything less than 1.4497 or something?
Yes, there is. And we'll get to it on this handout pretty soon. But I always like it when you guys ask the questions that will lead to it. So let's do this problem. Consider the car mileage case from previous sections. We found a sample of 50 mileages with a mean of x bar equals 31.56 and a standard deviation of 0.7977. Okay. In this situation, do we need to check to see if the sample looks normally distributed? No, because n is greater than 30. So let's find a 95% confidence interval for the population mean mileage and interpret it. So for this, just like we've done before, go ahead and try it yourself to make sure that you don't have any questions. don't forget to interpret it on yours too. So I found a critical point of 2.021. So my confidence interval goes from 31.3 to 31.78. So I'm 95% confident that the mean mileage of all the cars of this type, since that's my population that I'd be interested in, is between 31.3 and 31.78. Okay, questions on this. Were there any places where you got stuck? You'll notice as you do your homework that your textbook isn't very big on making you interpret it. I'm very big on making you interpret it, because otherwise, what's the point? So expect on the test I'll say things like, will you interpret it? And I expect to answer like this. So let's resume. We are talking about choosing our sample size. Okay, so we talked about how to choose our sample size for our Z confidence intervals. It makes sense that you might also want to choose your sample size for your T confidence intervals. So our margin of error for our confidence interval is defined as our critical point times S over the square root of n. We can rearrange this, solve it, and see that our equation is n equals a critical point times sample standard deviation over our desired margin of error. Okay. Now remember, if you want the length, if the book asks you for the length, you would have to first convert it to a desired margin of error. Okay. Yes, thank you. But now let me ask you this, okay? This is to tell us what sample size we need, okay? Before you take your sample, do you know your sample standard deviation? Okay. Or before you know how big of a sample to take, do you know what n minus 1 is to find your degrees of freedom in your critical point? No. Okay. So there's a few flaws with this formula to find our desired sample size. Okay. One of the ways that you can get around this is you can take a preliminary sample. So you go out, because we know it's expensive to take a really big sample, but you can go out and take a small sample and get an estimate of your standard deviation. Okay, and so you find your critical point for that small sample, and you find your estimate of your standard deviation for that small sample, and then you can figure out how big of a total sample you need. You could just do a completely new sample, or you could include your first sample in with your big sample too. So you might just need to know how many more people do I need. Okay, so a good example of this is last week I went to a lunch with my husband's work, and they were talking about how to do a research study. And they need to go into all the child care providers in Utah and rate them. But it takes them 3 hours per person to go rate. And we were telling them for the kind of sample they needed, they probably need at least 400 or 1,000 or a couple thousand people to go look at. And they're saying, there's no way that we can go look at that many people. Okay? At 3 hours apiece, this is going to take a really long time. So I tell them, well, you could go take a preliminary sample and maybe narrow down what you want to look at first with your preliminary sample, and then figure out how big of a sample you really need. Okay, so this is a good example of something you could do like that. So in our situation, we take a preliminary sample, a small sample, use it to find our critical point and a S, and then figure out how big of a total sample we really need. So a fast food company wants to estimate the mean waiting time for orders at the counter. A sample of 35 randomly chosen orders gives a sample mean of 1.7 minutes and a standard deviation of 0.9 minutes. Okay, so we are going to get to the margin of error. Let's just do the first part. So find and interpret a 99% confidence interval for our population mean waiting time. So first of all, you need to ask yourself, can I use this confidence interval? Okay, so do I start with a normal population or a sample size of at least 30? Okay, we have n is at least 30. Okay, so we're good there. So we need x bar plus or minus our critical point times s over the square root of n. So for my critical point, how much area for a 99% confidence interval, how much area goes in my right tail? Let's see, 99% That would give me 0.005 in each tail. So I need 0.005 in the right tail, and what are my degrees of freedom? 35 minus 1 is 34, and we will need to round down to 30. So someone look at your t-table that has it in front of you, and what is my critical point?
2.75.
Everyone agree with that? So that's kind of my preliminary work. So let's plug everything in. So my sample mean is 1.7 plus or minus my critical point of 2.75 times S of 0.9 over the square root of 35. So 1.7 plus or minus 0.39. Okay. So what my margin of error in this situation is 0.39 minutes. So someone tell me what I'm going to write to interpret this. Something like we
are 99% confident.
So we are 99% confident.
That our mean,
So 99% confident that our mean of what? What would be a reasonable population here? What do you think they're interested in? The mean waiting time for all orders? Is between those two values. So between 1.31 and 2.09 minutes. And then I didn't ask you this specifically, but what was our margin of error? .39. Okay. So for our next part for this problem, the company is unhappy with this margin of error. Okay. Because when you're dealing with minutes between 1 or times between 1 and 2 minutes, a difference of 0.39, let's see, 23 seconds, that makes a fairly big difference. Okay, they want their margin of error to be smaller. In fact, they want the length of this confidence interval to be less than 0.1. Length. Okay, how many more observations do they need? So first of all, for this length, what is our desired margin of error? Okay, so we want our length to be less than 0.1. What does that have to make the margin of error? Because your margin of error is the part you add or subtract, so your length is actually twice as big as your margin of error. So 0.1 divided by 2 is 0.05. Okay. So they want their margin of error to be less than 0.05. So our formula, see if I can remember it. It's our old critical point I'm just going to call it T star because it's an old critical point, times S over M squared. Is that correct? Since you guys can see at the top of the page. Okay. So what was my old critical point for my first sample? 2.75. What was the standard deviation for my first sample? 0.9. And our desired margin of error is 0.05. So square that. 2,450.25? Are they going to really sample a quarter of an order? Okay. No. Which direction should I round to make sure that I get that length less than 0.1? Okay, round up. So they need to use at least 2,451 orders. Okay. That seems like a lot of orders, right? It was a pretty big jump to get that small margin of error. Now in this situation, they could, because I just asked how many more observations do they need. They already had 35 observations. So 2,451 minus 35 is 2,416 more. Okay. So if you already have that data from the first sample, why not just include it in your total? So, any questions here? Now, here's where we get to talk about our one-sided confidence intervals. Okay, I'm just going to do the formulas for one-sided t, but you could do the same thing for a one-sided z just as easily. Okay, so sometimes we're not interested in our upper and lower bound. Sometimes we only need one bound. So we might be interested in just knowing, okay, is our mean waiting time less than this, or is our, I don't know, mean survival time at least such and such. Okay, so you might only be interested in one bound. So tell me, what do you think would change? So let's say we needed an upper bound. So you need an upper bound for 95%. Okay. So when I drew my picture, I only need my upper bound. I don't need my lower bound. Okay, so how much do I want still in kind of that middle area? I want my 95% to still be in that area. So I want the upper bound, so my 95% goes here. So how much is going to be left for the other part? 0.05. Okay. So now instead of having 0.025 in each tail, I just have 0.05 in only one tail. So instead of calling this T alpha over 2, it's now going to be a T alpha. Okay. Because I don't have two tails. Now again, you can try and memorize their formulas and memorize the notation, or you can just draw yourself a pretty picture and it'll probably be a little bit easier. Okay. So let's look at what changes in the actual formula. Okay, so for an upper bound, notice that your lower bound starts at negative infinity. That makes sense? Okay. X bar, notice you don't have, well, it's not plus or minus because I already put it in parentheses. So you start at negative infinity, and then your upper bound is plus T alpha n minus 1 s to the square root of n. Notice the only thing that changes is instead of an alpha over 2, that is now an alpha. Okay, because we only have one tail. Or if you want a lower bound, then it'll be the x bar minus T alpha n minus 1 s over the square root of n. But your upper bound will just be infinity. So, for example, a brand group is considering a new bottle design for a popular soft drink. They found a random sample of n equals 60 consumer ratings of this new bottle design. Let mu denote the mean rating of the new bottle design that would be given by all consumers. In order to assess whether mu exceeds the minimum standard composite score of 25 for successful bottle design, the brand group will calculate a 95% confidence lower bound for mu. Interpret this confidence interval. Okay, so they want to make sure that they're at least 25, which means that they are interested in a confidence interval kind of like this. And they want to find the lower bound. So they need 0.95 in the main part, and then how much is going to be left in that lower tail? 0.05. Okay. Let's see, we have an S, so do we need a Z test, or Z confidence interval, or T confidence interval? T. That means I also need degrees of freedom. So degrees of freedom is n minus 1. So n is 60, so n minus 1 is 59. What do I have to round that for on our table? The tables are different, so I remember what's on our table. What's the next lower degrees of freedom? 40. Okay, rounded 40. Let's see. When I go to my T table, we kind of have a problem, don't we? Because it only gives me areas in the right tail. What do you think I could do? Okay. Well, 1 minus only works with like areas, so I could try and say I have 0.95 area in the right tail, but it doesn't give me areas that big. But we could use our symmetry. Okay, so if I look up 0.05 in the right tail for 40 degrees of freedom, 0.05, I get 1.684, right? Okay. So, what did I just say, 1.684? Okay. Well, if you think about it, if this value was positive 1.684, then what would this value have to be according to symmetry, because the t-distribution is symmetric? Negative 1.684. Let's see. As far as my formula, I was calculating a lower bound. Okay. So my upper bound will just be infinity. So I'm going to need an x bar. Let's see, what I want, a plus or minus. I'm going to want a minus, or I guess since I did the negative, that's already worked in. But x bar minus my critical point, s over the square root of n. So x bar is 30.35 minus 1.684 times 3.1073 over the square root of 60 to infinity. Okay, so you can try and worry about whether you need a minus or whether or not to make this. By default, their critical value is always positive. Just make sure if you have a lower bound, then you make sure you minus, and if you have the upper bound, it should be addition.
So you just ignore the negative sign?
Yeah, well, because when I thought about it, I remembered that by definition, their critical value is always defined as the positive one. And so it would be minus a positive, or if you want, you can add a negative. Just make sure, since it's the lower one, that when you're done, this is a minus.
Repeat that again?
Okay, so by definition, critical points are always positive. So you need a minus, a positive value. Okay. However, the reason it works out is the whole reason you do a plus or minus is the top is positive, the bottom is negative. So because you want a lower bound, to get a lower bound, you always have to minus. So don't worry about your signs, just make sure that if you want a lower bound, that this ends up being a minus. Because you normally do plus or minus, make sure your lower bound is a minus. So this will change my final interpretation just a little bit, because now we are 95% confident that the mean rating for all consumers is what? It's not between two values anymore, it is at least or greater than 29.67. At least greater than, either way. Okay, so we're 95% confident that it's at least 29.67. What was their goal? Their goal was, does it exceed the minimum score of 25? So, do you think they made their goal of exceeding at 25? Okay. Yes, since we're sure that it's at least 29, so I think that they're good. So I guess questions on this part. Okay.
If we had I'm just trying to think if we used like the other side of 1.684, it would give us the same answer, wouldn't it? Because we'd have the same critical value, but it's like might be different.
So let's say you only wanted an upper bound for the same problem.
Oh yeah, I guess that wouldn't be upper bound.
Okay. Well,
No, still lower bound, like the left side of 1.684. You know what I'm trying to say? I can't think of how the problem would be stated exactly, but if we still use like the lower bound, but I'll think about it. I'll ask you.
okay, so think about it, ask me. So let me put an extra page in. Okay. If I was in the same situation and I wanted an upper bound, okay. So again, I draw the picture. Mostly I'm drawing the picture to make sure I figure out how much goes in the one tail. So I want 0.95, 0.05, and I'm looking for my upper bound. So what is my critical point? Since you guys have it in front of you and I can't look back at mine, the critical point was 1.684. Okay. And basically, rather than worrying about positives or negatives, I just say, okay, if I want an upper bound, then that means I don't care about the bottom point, so that would be negative infinity. I know I need an x bar, I need a critical point, and if I want an upper bound, because remember, it's always x minus and then x bar plus. Okay, so if I want my upper bound, what should my final sign be here? Plus. And I would just think about it more like that. Okay, and so we'd have negative infinity, and then x bar, what was my x bar? 30.35 plus my 1.684 times s is over the square root of 60, right? Okay. And so we could get an upper bound of 31.0255. Okay. Now, of course, in practice, you never find your lower bound and upper bound because you may as well just find your normal confidence interval. But that is what it would look like if you wanted an upper bound instead for some reason. Okay. Just remember that, again, your normal confidence interval, okay, is x bar minus and then x bar plus. Okay. And so if you want an upper bound, make sure you have a plus. If you want a lower bound, make sure you have a minus. Does that help? So for our last example, what if we have a data set for one person and the hours they spend per week on homework? So here's my data set, 10, 10, 9, etc. How big is our sample size? So go through, actually count up how many data points do you have? What did you guys get? 24? Okay. So Is that small enough that I need to check to see if I have a normal population?
Yes.
Okay, so check if population is normal. Now, I've said this a few times as we've gone through, we need to check to see if our population is normal. Now, you don't have all the data in the population, so how do we check if our population is normal? We check and see if our sample is normal. That's a good indication. So we need to check if sample is normal. Okay. So what do you think when you look at these graphical representations of my data? Okay. Let's see, my normal curve plot, definitely not a straight line. Okay, my box plot, notice how the median isn't close to the middle, so this is definitely skewed, and my histogram, you can see it is a very skewed histogram. Okay, so what would you say about this data set? Close enough to normal or definitely not normal? Okay, so this is definitely not normal. Okay, so we can't use a Z or T confidence interval. So whether or not you thought you might know the population standard deviation, you can't use a Z or T confidence interval because it doesn't fit the requirements. Okay. If you ever get in a situation like this where you don't fit the requirements, you can use what's called a non-parametric confidence interval. Okay. And that's something that we don't have time to cover in this class, but if you ever needed it in the future, you can know and you go start Googling non-parametric methods. Okay. So, any questions on confidence intervals? This is everything about confidence intervals. So we do have